Hello guys and welcome to another video of Grokking the Coding Interview series. My name is Parth, and in the series we are going through the depth first search algorithm at this point in time, and in this video we'll have a look at count paths for sum, which is classified as a medium problem. So let's look at the problem statement and try to implement a brute force solution. And they have also proposed an efficient solution which I'll be going over the next video. So let's try to implement a brute force solution for this problem. So given a binary tree and a number s, find all paths in the tree such that the sum of all the node values of each path equals s. Please note that the paths can start or end at any node, but all paths must follow a direction from the parent to the child. And here we have an example where the sum is 12, and looking at the explanation, we have three paths that add up to number 12. One is 7 5, second is 1 9 2, and the third one is 9 3. And we have another example of sum 11, and the output is we have two paths in this tree. One is 7 4 and the other one is 1 10. They both add up to number 11. So we get a sense of what is expected. Again, like in the previous problems, there isn't a requirement that it needs to start at the root node. It can start at any random node in the tree. However, it needs to go from the parent to a child. Okay, so it could randomly start here and go until here. It could also start at root and so on. So you see the number of paths we need to keep a track of in order to solve this problem is significantly more than if we had to only say check from root to leaf. So what is an approach which we can think of to start off to implement this problem? So one thing which we have to do is, as we are traversing say one side of the tree in the depth first search like manner, for example, if I'm traversing this tree from 1 to 7, and once I arrive at 7 here, what I want to do is I want to see, or for example, let's say I'm at 6 right now. So what I want to do at this stage is I want to see if any subsection of this traversal, for example, if I'm at 6, I can add up 6 plus 7, or 7 plus 1, or 6 plus 7 plus 1. So at this stage I want to try all the permutations of this path and see if it adds up to the sum which is required. So this is a check which I'll have to run at all of the nodes in order to make sure that I have the path. So one of the requirements right away is at every node I have to keep a track of the current path. So if I'm at 6, I need to know that I have come to 6 from 1 7 6, and only at that stage I can do this search and search for all the permutation of that path which might add up to say s. So we need to keep a track of all the paths. We need to run these searches, and once we are over with these searches, we'll have do backtrack. So for example, once I've explored this one, I need to hop onto 7 again and do the 5. So just trying to make sure that the path which I have with me right now is a representation of the current path I'm on. So once I'm over with the exploration here, I'll hop onto 7 and add this. If I keep 6 in the current path, it would lead to say wrong answers, for example. Okay, so we have to keep a track of all the paths. We have to do the backtracking, and this would pretty much be it when it comes to the baseline inefficient implementation, which is O of n squared. We do have an O of n implementation here as well, but we'll look at it in the next video. I'll make sure to link it up if you're watching this video at the later stage. Okay, so let's go ahead and try to implement a solution which would work to start off with, and then we'll move on to optimizing things. Okay, as we have been doing with most of the implementation, we want to implement a recursive function at this stage. It's recur. We want to provide the root, we want to provide the sum, and we want to provide the current path as well. Just one quick heads up here, like one of the things which we are not considering here, I mean, again, I'm not sure, like I think it should not make a difference, as we'll be able to check it, but please expect that these nodes can also contain negative values, so there might be some edge cases that we would want to brainstorm in that scenario as well. Okay, so let's go ahead with the implementation. Paths, recur, current node, sum, and the current path. So let's go ahead and handle the base case. If current node is none, we simply return 0, and we sign out of the algorithm. We return that the number of paths that add up to that number is 0. Okay, so first thing first, we want to append the current node in the current path. So current node.val. We want to define two variables at this stage. Path count. In here we'll keep a track of the number of paths which add up to that sum, and we want to define a path sum as well, where we'll go and validate if any of the subtrees add up to that number. And what we want to do is we want to traverse the current path and see if any of those sub elements add up to that number, and the traversal is pretty interesting. So let's have a look for index in range, length of current path -1 -1. So we are defining the length of say the for loop, how many iterations we want to do, where would we want to stop. So we want to start at the final, so we are basically starting at the end of the current path, and we want to stop at the final element as well. So for example, this is our path. Then essentially what we want to do is we want to start here, traverse this with a step of -1. So we want to go one step below or one step less. So we are decreasing the index as we are traversing, and we want to simply stop at this final element. So this is what this for loop is all about. A very simple a very simple maneuver, but again, the way we define this loop is it becomes really important to explain if you're working in other languages. So at this stage, what we want to do is we want to take the path sum and update it with the current path, and index in the current path with the current index. So what are we accomplishing here? Let's add another statement, and then I'll explain what we are trying to do here. So if path sum is equals to s, we increase the path count by 1. So what are we trying to do here? So let's have a look at this example here. So for example, if we are at 4 at this node 4, the current path is essentially 12, 7 and 4. So what I'm trying to do here is I have a variable which is path sum, which is 0 at this stage, and I start with adding 4 in it. I check if 4 is equals to the sum which has been specified here, 11, which isn't the case, so I'll skip it. I wouldn't update the variable here. Then I'll add 7 in here, so it'll become 11, and 11 is equal to the sum which we need here, so I'll increase the counter, and then we will add 12 in it, which is more than of course 11, hence I wouldn't increase the counter. Now the interesting aspect to understand here is, why are we doing this reverse traversal of the list? I mean, if you look at the statement here, it said the path can start at any node, but it needs to have a direction. So it needs to start from the top and go to the bottom. So essentially we want to check, or we want to add these numbers starting from the later end of the node and check if any of the subsequent paths add there. And in the cases where, for example, this would have been, the path will already be checked or will already be evaluated once we are on node 7. So we do not need to do those checks in this recursive call to start off with. I hope I'm making sense, but again, feel free to write a comment in case it was not clear. I'll try to make it more clear in the next video. So it is what we are trying to do here, and once we have identified the number of paths that add up to the sum, what we want to do is we want to traverse the left subtree and the right subtree and find number of paths as well, and then we want to do a backtrack and end our algorithm there. So the path count plus this call, again, I'll just get this from here, which is easier. We want to do it for left, path count plus equals, and we also want to do it for the right, and we want to delete the last element of the current path once we are about to return, and we do a return here of the path count, which will be returned as the final solution for our implementation. So let's try to run it in case we made any mistakes. A tree has 2 paths. Let's see which tree are we speaking about. 12, 7, 1, 4, 10, 12. Okay, so the answer is 2 paths. So, okay, it looks like our implementation is correct. There aren't any specific errors. Let's quickly jump into the space and time complexity explanation and try to understand what it is about. So the time complexity of the above algorithm is O n squared in the worst case, where n is the total number of nodes in the tree. This is due to the fact that we traverse each node once, but for every node we iterate the current path. But for every node we iterate the current path. Yeah, that's that. The current path in the worst case can be O of n in the case of a skewed tree. Okay, so if we have an imbalanced tree, the worst case can be O of n, where we have to just explore all the nodes in one branch of the tree. But if the tree is balanced, then the current path will be equal to the height of the tree, O of log n. So the best case of our algorithm will be O n log n. Okay. Okay, so this makes sense. Let's also look at the space complexity. The space complexity is O of n. The space will be used to store the recursion stack. I mean, it is a very standard explanation. So in the worst case, it can be a linked list, and hence you'll just simply have to save all the calls in the recursive stack. And we also need O on, yeah, so it will be O of n plus n, which will be O of n. So yeah, so we went through the space and time complexity. I hope it made sense, but let me know in case there are any questions. We do have a more efficient solution here, which is O of n. We'll have a look at it in the next video. Until the next video, have a great